whole section is an ellipse 52.5 feet by 26.25 feet, or an area of 1,076 square feet. The maximum speed of the airflow is 112 miles an hour, which corresponds to an intake of 6 tons of air per second. The experimental chamber, which is apparently light in construction, is subject to a partial vacuum as compared with the surrounding atmosphere. At maximum speed, this partial vacuum means a stress of 32 pounds per square foot on the walls of the building. We can catch sight of the outlet cone and of the set of 6 fans which cause the suction through the meshes of the honeycomb. The outlet cone opens out into the suction chamber, which is a huge nave 141 feet wide with a wall 85 feet high perforated by 6 cells in which the fans rotate. The purpose of this chamber is to keep steady the partial vacuum set up by the rotation of the fans. Great difficulties attended the building of this structure on account of the traction of the air screws and of the weight of the electric motors. Each of the 1,000 horsepower motors weighs 18 tons. Each fan has 10 wooden blades. Their diameter is 28 feet 6½ inches. Their weight 5 tons, and their maximum rotational speed is 300 revolutions per minute. The traction at this speed is 3½ tons. The clearance between the blade tips and the cell is of the order of 0.4 of an inch, implying great constructional precision. The total power, amounting to 6,000 horsepower, absorbed by the 6 fans, is provided by 2 electric sets essentially constituted by a 15,750 volt 3-phase synchronous motor and a 0 to 600 volt direct current generator. The plant is controlled from the instrument chamber, where a switch desk makes it possible to regulate the speed of the fans. The airflow escapes into the atmosphere at reduced speed over an area of 3,767 square feet. This tunnel, built in the open, is located in a very sheltered spot so that the natural winds may not disturb its operation. Gazing down from the highest point of the tunnel, we see that the chalet grounds are surrounded by thickly wooded hills. As the air is sucked in from and forced out into the atmosphere, the airplane undergoing test is exposed to a continually renewed airflow. Moreover, if the test is made with the engine running, the exhaust gases are completely evacuated. Let us now return to the experimental chamber, for we are about to witness all the stages of an actual test. This is a particularly interesting model, representing a 4-engined airplane with retractable landing gear. This is intended for transatlantic transport and is to weigh 25 tons. The model, which is a faithful reproduction, reduced to 1/3 of the natural size, has a span of 33 feet. This model is about the size of a touring airplane and is designed for actual flight. Systematic experiments, carried out first in the tunnel on small and large models, and then in flight with the latter, considerably facilitate the designing of the final airplane. Although costly, this method actually results in a real economy, considerably reduces the risk of test flights, and very considerably shortens their duration. This particular model is equipped with dummy engines, which are exact reproductions of those of the airplane. cowling surrounding them can be arranged for the study of cooling phenomena. Variable pitch three-blade propellers make it possible to experiment various rates of operation in flight on the model itself. Electric motors drive the propellers so that torque and traction can be measured. Such tests necessitate the presence on board the model of a test pilot. To take the readings of the numerous measuring instruments, to regulate the propeller speeds, and operate the controls. The airplane itself thus becomes an actual laboratory. Here is the positioning of the model for the purpose of carrying out the experiment. The plane is first fixed at the desired height on a metal structure carried by an overhead traveling crane, and the whole assembly is moved into the axis of the tunnel and positioned in the center of the airflow through the experimental chamber. The frame itself is secured to a platform connected with the balances located in the basement. The airplane is supported at 3 points. 2 of these enable it to pivot about a pitching axis passing through the center of gravity, G. The third, which is positioned at the rear, is rendered movable by a telescopic mast, which makes it possible to vary the angle of attack of the airplane in the wind. A dynamometer is positioned between the telescopic mast and the airplane, and its indications provide data concerning longitudinal stability. The platform supporting the frame is pivoted like a turntable, thus making it possible to expose the plane obliquely to the airflow. This platform, which is isolated from the floor of the experimental chamber, has an extension into the basement. In the form of a metal structure provided with 3 legs connected to a set of 6 balances. It is obvious that the airflow tends to lift the airplane and to force it backwards, but as it is held in position, the corresponding forces are applied to the balances. The 3 balances positioned under the feet of the support measure the lift. 3 other balances are submitted to the horizontal forces. 2 of them measure the drag. And the third, the lateral force, if any. These balances are interconnected by devices which ensure the functioning of the assembly as a whole. The weighing operations are carried out simultaneously and automatically. Assistants merely attend to the resetting of the balances. A counterweight moves along the beam of a balance and comes to rest when equilibrium is reached. A continuous stress recorder is also used. Let us now watch a test. Electrically operated winches open the doors closing the intake cone